All right, so the first videos in this series, we talked about establishing the fact that the Earth was round, except that it's not quite. It's round-ish, right? So we're going along. We figure out the Earth is round. We figure out how to measure it. We sail around it a few times. We do a couple of other things. By the time we get to the 18th century, Isaac Newton, who you might recognize from other science classes, figure out that the Earth is actually a spheroid rather than a perfect sphere. Or an ellipsoid. So spheroid, ellipsoid, pretty similar. And basically what's happening is as it's spinning around its axis, it's just sort of getting a little wider in the middle, right? Many of us experience that as we get older. The Earth is pretty old, so that happens too, but mostly it's the spinning motion that's causing it. So in addition to that wider in the middle problem, the Earth is also not a smooth surface. It's bumpy. And so we've got, a sort of a model here. We've got the surface of the land, this bumpy, lumpy object here. We have the geoid, which is essentially mean sea level that we use to sort of average out all of that bumpiness. And then from that, we create a series of mathematical ellipsoids. And I'm going to come back and talk about those in a minute. But first, I want to have a little moment here with Neil deGrasse Tyson. And
To the astrophysicist, we don't really care much about sea level.
No.
If you want to be high, you're measuring your distance from the center of the Earth.
From the very center of the Earth.
Is that different from the center?
I'm trying to
Okay,
give it...
the very center of the Earth. So you want to find the farthest point from that center. And it turns out sea level at the equator is farther away from the center of the Earth than sea level near the poles. It has nothing to do with global warming and melting of the ice caps.
Why is that?
Because Earth, we know it spins once a day. Yes, thank you. 3 people know how long a day lasts here.
Good for row number 2. They're off to a great start.
So you spin, when you spin pizza dough, it kind of flattens out.
Yeah.
Gets wider in the middle. And so Earth, throughout its life, even when it formed, it was spinning. And it got a little wider at the equator than it does at the poles. So it's not actually a sphere. It's oblate. And officially it's an oblate spheroid. That's what we call it. But not only that, it's slightly wider below the equator than above the equator.
A little chubbier.
A little chubbier.
Yeah.
Chubby's a good word. It's like pear-shaped.
Yeah.
So it turns out the pear-shapedness is bigger than the height of Mount Everest above sea level.
How much higher is the tall mountain that you identify in this book, which name I forget, and probably you do too, in Peru, or is it Ecuador?
Ecuador.
Ecuador. How much higher, if you were on top of this mountain in Ecuador, how much higher than the Mount Everest would you be?
There's a 20,000-foot mountain in Ecuador, which is right. Ecuador is like near the equator, hence Ecuador.
Oh, you're just not giving up.
And that mountain is actually, the summit of that mountain is 1 1/3 miles higher away from Earth's center than the summit of Mount Everest.
Okay. Question number 2.
But you got to know, let me just so you understand. We've been fed a lie our entire, I want to call it a lie. We've been fed.
It's a point of view thing, I think.
We've been fed Earth has been misrepresented to us by geologists. Because the globes that you buy, that you rub your fingers over it, and you feel the Himalayas, and you feel the Rocky Mountains. No. No, okay? These mountains are puny compared to the size of the Earth. You would not know they were there. If you were truly that size, some big cosmic giant lumbering through space, coming upon the Earth, rubbing your hand on it, the depth of your, what do you call these things?
Your finger...
The fingerprint mark, the depth of that would be greater than the entire range of distance from the Marianas Trench in the bottom of the Pacific to the top of Mount Everest. Therefore, you would close your eyes, rub your finger, you would not know whether you are on ocean, valley, mountain, or hill.
Well, you might be wet or dry. You might be,
Well, by how much wet?
A little.
How? No.
Yes.
You wouldn't even notice it. You're not going to say, oh, I got to dry my hand. The depth
Yeah.
of the ocean doesn't measure up to the depth of your fingerprint. That's my point.
Oh.
So we've been fed this misrepresentation of our own planet on the belief that, in fact, we have real surface features. But cosmically speaking, we're practically a perfect sphere.
So basically, the Earth, cosmically, if you were to take a cue ball, right, from a pool table and blow it up to the size of the Earth, it would actually be bumpier than the surface of the Earth. But to us, puny humans running around on the Earth, we see the terrain changes and we want to measure those and we want to think about those. So, going back to the representations of the Earth, we've got the bumpy surface of the Earth here, right? Which is the real surface, so that's the Marianas Trench and Mount Everest and all of the other mountains that we measure along the way. Then we've got the reference geoid, which is mean sea level, which is not the same height all the way around the Earth, so that's why you'll see it here. It's a little wavy, but it's much smoother than trying to calculate for all the mountains. And then we have the reference ellipsoid. And when we're mapping and calculating coordinates and position and everything else, we're going to use a reference ellipsoid because it's a mathematical approximation of that shape and therefore much easier to work with. So we already talked about latitude and longitude as a coordinate system, and I'll talk in a second about what that's based on. But the reference ellipsoid is the thing that matters to us when we're making maps. So this is a definition that you need to sort of hard code into your brain in some way, and find a way to make it meaningful to you. It's a little bit of a weird term, and it's kind of hard to wrap your head around it. But a datum is the base of every coordinate system that we use. And like I said, we're going to talk more about those later on in this course. But for right now, we just want to think about the baseline because this is how we're measuring the Earth. So a datum is just a standard reference system or a reference ellipsoid. I've already talked about reference ellipsoid, right? That mathematical approximation. And most of the ones that we use are based on an ellipsoid, but sometimes it's a point rather than that. And so I'll go through a couple of examples here, but it's from that reference, we then can figure out where we are on the Earth. So here's an example of one that's based on a point rather than an ellipsoid. And this is NAD 27, which stands for North American Datum 1927. And it is based on a point on the surface of the Earth in Kansas, right? It's Meads Ranch in Kansas. And essentially what happened was they took a point and they started doing a standard land survey away from that point. So they started measuring away from that, and then at some point they stopped measuring and then just calculated the rest of it. So if we have this green circle here as the lumpy surface of the Earth, and then here's our datum in Kansas, and then we calculate this ellipsoid, you can see that by the time you get to the other side of the Earth, it's going to be pretty wacky, right? It's just not going to match very well. So it works super well over here in the area that it matches, North America, right? Hence the North American datum. But gets a little out of whack when you get to the other side of the Earth. And this is one of the most important things about datums is you need the right one for the task at hand. So NAD 27 worked pretty well for us for a while. But then we decided that we needed to move on from that. So we figured out how to fling things into space. And when we started flinging things into space, we also figured out how to measure the Earth a little bit better and to actually calculate where the center of the Earth is. So we get better at surveying, right? The survey equipment gets better, the techniques get better, we get computers that can crunch the numbers faster and everything else. And then we stop optically surveying the Earth from a single point, and we start doing a mathematical survey based on this calculation of the center of the Earth, which we can now find because we have chucked things into space and looked at the planet and taken measurements from there. So Kansas doesn't cut it anymore, so we need a new system. So now we have the WGS 84 ellipsoid, which is the basis for quite a few coordinate systems, including what we typically use when we're calculating latitude and longitude. So WGS 84 has its origin at the center of the Earth, right? We have the lumpy surface of the Earth here, and then we have this nice smooth ellipsoid. And you'll notice that because it's based at the center of the Earth rather than a single point, it doesn't have that huge gap where it doesn't match, right? So it's closer in more places, and in the places where it's not very close, it's not as far off as the other one, right? So because the origin's at the center of the Earth and it works pretty much all over the globe, pretty universally, this makes it ideal for a global positioning system for GPS coordinates, right? So the most common coordinate system coded into GPS is WGS84, and we'll come back and hit that when we talk about GPS again, but just kind of stick that in there, stick that information in there for later. Okay, so here's a sample of some of the ones that we use most commonly around here. So NAD 27 is that first one that we talked about, right? It's designed for North America. It's based in Kansas. And it's based on this Clark 1866 ellipsoid, which is that manually calculated, optically surveyed ellipsoid that is on the surface of the Earth. Why do we still have it if we don't use it, right? If it's not good anymore? Well, we still need it because there's an awful lot of maps that were created in it, and we need to know how to translate those maps. So if you're working with county data and older county maps, there's a pretty good chance that they're going to be in NAD 27. And that actually can pose a problem later, and I'll come back and talk about that in a second. But there's two more here that we use commonly in North America, and that's these two in red, WGS 84 and NAD 1983. So WGS 84, like I said, is the basis for a lot of global systems because it's, as you saw in the rather crude drawing there, it's pretty good almost everywhere. We have another North American tailored one, and that's also a center of mass based ellipsoid, right? That particular ellipsoid happens to be called GRS 80. But it was sort of tailored to fit North America and the Caribbean a little bit better than other places, right? So again, North American datum, 1983. And just as an example of another one that is surface of the Earth based, the European 1950 datum, which is based in Potsdam, which does Europe, the Middle East, and North Africa, right? So what I want you to take away from this chart, you don't have to memorize the whole thing, is I want you to predominantly look at these three that we use in North America. So NAD 27, WGS 84, NAD 83. And I want you to know where they're good for. So North America for 27, global for WGS 84, and then North America again for NAD 83. And then also the basis, right? So NAD 27 is surface of the Earth or Kansas or Meads Ranch, any of those should sort of stick in your brain. And then the other two are center of mass, okay? So I gave you the European one as just an example of another surface of the Earth. Don't worry about memorizing that one, but do think about these three, the area that they're used for, and then whether they're surface of the Earth or center of the Earth, okay? The rest of these details are things that you can look up. All right, so we have these datums. They're great. We completely revamp when we learn new science, but we also just update these, right? So WGS 84, which has this identifier code of G1762 that you'll notice if you're in ArcMap and you dig into the details, you'll see this. The current epoch is 2005, right? So this has been upgraded from 84 a number of times until the epoch 2005. That happens to be the most current one of that one. And that has to do with, again, improvements in technology, improvements with measurements of where the center of the Earth is, and recalculating that ellipsoid. The original NAD 83 was actually created in 86, so this is a little bit like Windows versions, right? Like Windows 85 didn't come out till 86 and whatever, or Windows 95 didn't come out till Windows 96 or till 1996, etc. So the numbers don't quite match up with the years, but that's okay. There's a 1992, a 2002, right? So every so often they update, and currently we are on the 2011 version, which happens to be epoch 2010. Don't have to memorize those either. Just pay attention because these adjustments, these are more subtle than picking the wrong datum, but there is a difference, right? Here's an example of the NAD 83 adjustment from the original in 86 to the 2000s. It's moved about 4 feet. On the other hand, if you pick the wrong datum, you're going to wind up with a big shift, right? So NAD 27 and NAD 83, and this is calculated in meters. Oftentimes you'll see those two calculated in feet because it's the United States and we're still using feet, right? In the Midwest, it's not so bad. But you get out here to California and there's something like an 80-meter difference between the two systems. So you might be thinking, hey, that's a pretty large area, so that might not be such a big deal if I'm doing this locally. But here's what happens if you pick the wrong system on your GPS unit. This is someone was going out and collecting data for individual houses for the fire department in Oregon, which, of course, right now, super critical that we know where all the houses are. And if you pick the wrong datum on your data when you pull it down, it can be off in a significant way, right? So in this particular case, it was off 700 feet. And you can pretty easily see that when you lay it on the map here, right? You can tell that these are kind of the roads, right? This little bend here corresponds with this little bend, this little loop of houses, right? This zigzaggy loop here goes with this zigzaggy loop over here. So super critical to have the right datum for the job, which means paying attention to your metadata and paying attention to your settings when you're pulling in data from other things. All right? This one got a little long, but that's it for this section. So thanks for listening.